good morning. So, yeah, I'm going to talk about the impact of stellar activity on the transmission spectroscopy. So, this is the outline. At the beginning, I will briefly talk about the transmission spectroscopy method to study the planet atmosphere, and then I will talk about the stellar activity and how it can affect the transmission spectroscopy. So when a transiting exoplanet transits its host star, the total brightness of the system shows a reduction, which is known as a transit light curve. And one important information which we can get from the depth of the transit is the planet radius. If we observe the transit in the different wavelength, we are able to derive the planet radius as a function of the wavelength, which is known as a transmission spectra. And by analyzing the transmission spectra, which is the variation of the planet radius as a function of wavelength, you can interpret it as a presence of the atmosphere in the planet. And also you can put some constraint on the atmosphere models, for example, like on the molecular composition and also the thermal structure in the atmosphere of the planet. Here I'm showing one of the most well-studied exoplanet, HD 189733b, which here you see the transmission spectra obtained by HST and Spitzer and also from ground. And you see an increasement in the planet radius toward the shorter wavelength, which was interpreted as a presence of the Rayleigh scattering in the planet atmosphere, or in other words, the planet should have an atmosphere with a blue sky. But when the planet transits their host, they are not transiting a uniform disk. The star usually have some feature on their surface, such as a spot and the plage, that they are the bright spot, which you can see here, for example. So these feature can affect the transit light curve, so they are not as symmetry or perfect as I showed at the beginning. Those features can affect the transit in two ways. One is that the transiting planet don't overlap with those features, so the total flux of the star is different, and it was shown that those can affect the planet radius measurement up to 4%. So we are overestimating the planet radius because of non-occulted stellar spot. But in other situations, the transiting planet during its transit can overlap with those features, which can introduce some anomaly in the transit. Those anomalies also can cause difficulty in measuring the planet radius. Usually people, in order to analyze their light curve, decide to remove those anomalies and study the rest of the light curve, which we show that it's not the best approach because you are introducing some biases in your measurement. So in order to analyze those light curve which has the anomaly, we developed a code named SOAP-T, which can simulate a transiting planet over the spotted star and can produce those anomalies inside the light curve. So in order to see how much those anomalies are affecting the planet radius measurement, we generate a large number of mock transit observation with those anomalies, and then we try to obtain the planet radius and see how much the value that we obtain from the fitting is different from the actual value. And we consider the overlap of the planet with the bright spot and also dark spot. So it can cause these positive bumps or also negative bumps, which the positive bumps cause the less radius of the planet, the fitted one, and in the other one, you are overestimating the planet radius. The interesting result was that those features, due to stellar activity, can cause 10% overestimation in the planet radius, especially in the shorter wavelength, and also around 6% underestimation by overlapping with the spot. So this was very interesting because if we go back to the famous planet, which they observed the increasement in the planet radius toward the shorter wavelength, This planet is orbiting an active star. The stars show up to 2% variation during its rotation around itself. So it shows that the star should have a lot of spot or plage on the surface of it. So by assuming that the HD 189733b is transiting over one of those features during its transit, we could easily reproduce the transmission spectroscopy that was observed. So we are not claiming that, okay, that planet does not have an atmosphere, but we are saying that the amplitude of the Rayleigh scattering or blue sky feature that you expect to see in your transmission spectroscopy can be easily mimicked by the activity of the star. And as a conclusion, before analyzing and interpreting the transmission spectroscopy to put constraint on the planet atmosphere, we should be sure that we correct the impact of stellar activity.